Hey, everybody. My name's David Gisson. I'm the interim director and associate professor in the architecture division. And we're also very happy to have our very own Mauricio Soto in the house tonight. So I see a lot of familiar faces out there. And as many of you know, Mauricio is a professor here at the California College of the Arts who has a specialty in the design and construction of lightweight structures. And as an instructor, Mauricio is definitely one of our most dedicated colleagues, so particularly excited about this talk. As many of you know, the students know, from your architectural history courses, lightweight structures can be traced back to the earliest forms of human settlement. Yet I guess since the 30s or 40s, Mauricio, they've become a more critical part of like American and European vanguard architecture, right? Okay. So in Germany and Austria, where Mauricio is taught, lightweight structures have a very strong affiliation with a kind of high-tech research and high-tech culture. But it's great that Mauricio is here in the Bay Area now, because here is one of the key places where lightweight structures came to mean something else. Here they became intimately associated with the counterculture and was more subversive architectural practices. And so it's always interesting, like, why did anybody ever see those buildings as being subversive and radical? But I guess it's because you can build them and destroy them and the public spaces within them very quickly, right? So as someone who's taught in Germany and Austria, but is now at CCA, Mauricio is uniquely positioned to straddle these two contexts, right? And we all hope you develop this more subversive approach, right? Okay. So anyway, before joining CCA, Mauricio worked in several architectural offices throughout Europe. He was involved in the design of the membrane roof for the Norway Pavilion at the Expo 2010 in Shanghai, the deployable umbrellas for the Medina Mosque in Saudi Arabia, and the Spiky Pod, which is a great name, inside the Queen Mary Hospital in London. Mauricio also taught architectural design, building technologies, and materials at the University of Stuttgart, Germany, and at the TU in Vienna, Austria. And in 2005, he founded his current company known as Studio LD. So just to wrap this up, Mauricio graduated with honors with a professional degree in architecture from the Universidad de los Andes, Venezuela in 1999, and he completed his Master's of Architecture degree from the University of Michigan in 2003, where he was awarded the 2001 Alumni Society Award. So please join me in welcoming Mauricio.
All right, let's see how this works. Okay, well, I would like to thank David Gisson, for the invitation to participate in our own lecture series. This is for me a really special opportunity. Normally, in lecture series, we typically invite people to come from other places around the country and around the world to come here, and our faculty also travel some, other places to present their work. But for some reason, it doesn't happen very often that professors have the opportunity to actually talk in their own schools. And for me, being a relatively new faculty member, this is a really special opportunity because it allows me that gives me the chance to kind of introduce myself and introduce my work to the entire architecture community at CCA. So instead of coming here and just kind of showing you a series of random individual projects that perhaps might or might not be related to each other, I thought it was more important to actually talk to you a little bit more in general about my professional philosophy, both as an educator and as an architect, and only then show you a couple of projects to hopefully will kind of showcase my interests. So the title of my presentation is Designing Materiality. This title encapsulates my professional interest in general. It describes part of my teaching and professional philosophy. And of course, it has to do with process, with the way we architects develop ideas, with the way we architects work. So today, in order to develop ideas, we architects typically work with abstractions. This is pretty clear. We work with artifacts. And these have been traditionally drawings and models that by definition, they refer normally to something else, a construction or a building that might or might not get to be built. And as useful as these abstractions are, they also have two major limitations. One of them is obviously scale, and the other one is materiality. We cannot possibly encounter the spatial and behavioral properties of the materials these abstractions, these artifacts represent, or really fully experience the real consequences, the physical consequences of our designs through this means of representation alone. In addition, this particular way of working, this separation between an architect and somebody who works with abstractions and designs versus somebody who also builds, has influenced our understanding of what architecture truly is. So in most cases, we believe architecture to be more about this abstract speculation of ideas, this development, this thought process that has to do with the way we perceive space. And in many cases, that might not have too much to do with actually building. Nowadays, typically, we consider design and building to be two perhaps related, but also very distinct individual activities. This, of course, was not always the case. Throughout ancient and medieval history, most architectural design and construction was actually carried out by artisans. So these have been typically masons or carpenters. And until modern times, there was no clear distinction between an architect, a builder, or even an engineer. In fact, in Europe, those titles were mainly geographical variations that were applied, or that often described exactly the same person. And in fact, nowadays in Germany, for example, where I worked and taught for many years, architecture students and engineering students, they actually graduate with the exact same title, diploma ingenieur. So on architecture students and engineering students, they can actually take classes with each other. So I actually taught, for example, design studio to many structural engineering students. In the US, however, a typical architecture school will include within its programs architecture, interior design, or interior architecture, landscape architecture, urban planning, but they will also kind of distinguish themselves from other professions that have more to do with materiality, such as, let's say, structural engineering or material science. And in fact, I find it really interesting that when I came here a year ago, a little bit longer, I realized that here at CCA we have a lot of MFA students, sculpture students. We also have furniture design students. And in their case, that clear distinction, that separation is not that strong. I mean, because of scale, sculpture students and furniture design students, they actually have the chance to design by making. They have they design by being in direct contact with building materials, which I think they have an advantage in the way they work. After all, the word architect really comes, from the Greek architekton, which really means chief builder. So it's not chief speculator or chief philosopher or chief, it's really chief builder. At least that's what the name is supposed to mean. Now, so how did this distinction between, again, a professional designer versus somehow a hands-on, the distinction between an architect as a professional designer, an intellectual designer versus in contrast with somebody who's a craftsman who is somehow hands-on, came to be. Well, I'm not a historian, but it seems like people seem to agree that various developments in technology, such as introduction of linear perspective, instruments for drawings, and the use of projections techniques to describe a three-dimensional object in 2 dimensions, allow for this to happen. So all of a sudden, architects could spend their time just drawing and planning and speculating without necessarily ever having to interact with the physical world. And of course, these allow the discipline of architecture to broaden up and include other concepts previously believed to belong to the realms of art or history or philosophy, which is absolutely fantastic, don't get me wrong, it's truly liberating. But I will argue, however, and this is something really important, that in architecture school and in architecture in general, some people tend to believe that technical questions can actually limit creative freedom. So some architecture students, I've noticed that they tend to, to think about technical issues such as, let's say, structural stability or manufacturing processes or building materials or detailing, basically has problems. These are problems that they need to be solved after the main concept of a design is already established. They consider these topics to have nothing or very little to do with creativity and design. And in fact, it's interesting to notice that recent graduated architects are typically well known in the industry for knowing very little about construction, when they go out to the real world. So my teaching and professional philosophy is basically based on the premise that materiality and creativity, they do not have to be mutually exclusive, but they should in fact support and reinforce each other. So understanding the potential and limitations of construction materials, being responsible for the structural stability of a design, and being familiar with contemporary manufacturing and installation processes are in themselves abundant sources of creativity, and actually should be an integral part of the design process. So I have tried to explore all these issues in my career, all the way since I was a student, now as a professional architect and also as an educator. So now the first project I want to show you is my undergrad thesis that I did already 15 years ago when I was back in Venezuela in 1999. So I was born in a small city called Merida, which I got these laser pointers so that I can actually do this. It's here. So you have here Panama, Venezuela, Colombia, and you have the Andes, this big series of mountains going this way, all the way from Ecuador, Colombia, and then they go this way. When the mountains get here, they're not that high, but they're still about, 16,000, 15,000 feet. Now, this is how the area looks like. What is interesting is that normally when I show these pictures around, people say like, wow, this is really beautiful. But of course now, since I've been here in the Bay Area, I get the feeling that I'm not gonna be impressing anybody because this area is so beautiful. So in any case, the city has about 100,000 people, and it's basically jammed up in the Andes. So we have huge mountains coming this way. The city is really narrow and really long. We have a river going all the way through the city, which is the Albarregas River. And down here we have another river, which is the Chama. And then here you cannot see in this picture doesn't show it, but we have really high mountains going all the way again to 15,000, 16,000 feet. So you can see here the plan drawing of the city is barely a couple of kilometers wide and really, really long. So you can imagine the amount of the traffic jams that that there are in the city. We only have there's only a couple of streets that go in this direction, and the university, for example, where I went to undergrad, is in the north part of the city, and everybody lives in the south part. So it's terrible, the traffic jams. So at the time, the idea was to somehow to propose some kind of system of public transportation, and what it was proposed was to basically use the valley of the Albarregas River to design some kind of high line or some kind of elevated, let's say, train system like a subway or something. So I decided to basically design one of the train stations. And that was my undergraduate thesis. It was a professional degree, so you had to do a thesis. And it wasn't really that much conceptual as, let's say, a master thesis is here. CCA or at the University of Michigan where I went to. But it was more a way to for students to round up their career and show, let's say, their expertise, at least technical expertise. So this is the train station that I designed. It's very simple. It was basically a tube with a series of elements. This was basically a parking structure. And as you can see here, the quality of the space was based on the expression of the construction materials, on the expression of the structure. At the time, back in 1999, Venezuela was a kind of world-class exporter of steel and aluminum, and it was thought that the extensive use of this building material could, create in Venezuelans a sense of kind of national pride and kind of try to bring the economy up. So here we see an elevation and a section, and here we see a couple of plan views. So this is the platform level, and of course I was really, as you can see, the rails, they depict one of these elevated magnetic train systems. So I was really, pushing, the technology aspect. Right. Something that was very important for me is that the whole area, all the valley of the river, was extensively covered with really a lot of tropical vegetation. So on plan view, this is basically the street level. So it was important for me to separate the station from the street and basically map the position of every large tree and generate between the platform and the street a series of access piazzas that were also somehow shaded by the local trees. So this is the physical model that I created. You can see the piazzas here and here. This was all done before laser cutter, so a long time to cut all of these pieces by hand. Okay, so in 1999, after graduation, I had the chance to work in a local tensile membrane structures and transformable structures office called Grupo Estrana. This was in Caracas. So before I actually went to pursue graduate studies at the University of Michigan, I decided to work there. And one of the projects that I was involved was called the Estran module. So this was basically a deployable structure designed to rapidly provide shelter to areas affected by natural disasters. That was the main idea. And also exposition spaces or temporary deposits or outdoor gathering spaces and any other space that required being rapidly covered or protected. So the whole thing weighed about 2,000 pounds. It was made of aluminum, and it covered an area of about 2,100 square feet. And the nice thing is when it was closed, when it was collapsed, the whole structure, the dimensions were about 2 feet by 4 feet by 15 feet tall, so it was really, really compact. Yeah, so again, it was made out of aluminum, and all the connection details were galvanized steel. And the membrane was a polyester base membrane coated with PVC, which is the standard. And of course, it was hanging within the structure with a series of pulleys and cables. So the whole structure was designed to be held from the top by a crane. The crane is actually not really necessary to lift the structure, but it was there just to reduce friction. So you can see, this is basically 4 of us. This was done, by the way, in the person in charge of the office was Carlos Enrique Hernandez, who went to MIT and worked with Wacław. I never know how to say this name, but I'm sure you know Wacław Zaleski, who was teaching structures at MIT for many years. He's still alive. He's like 96, but obviously retired. So in any case, so the crane is basically holding the structure from the top, and 4 people, they grab each one leg and they open the whole structure up. And there is a point where the crane really has to hold it. There's just one point right here when the structure is totally unstable. So here is stable, here is totally unstable, and here it becomes stable again. So there's one point where the crane is really necessary. And then once it's locked into position, then the membrane is installed. So we did this and we realized, well, this is great, but if this structure is supposed to be servicing, let's say, remote areas after, let's say, an earthquake or something like this, the question is, well, what if you cannot get the crane in? So what we did is we designed a very simple kind of a series of skates with wheels, and to basically be able to hopefully install this thing without any cranes. So of course what that meant is that talking about tolerances, in my classes we always talk about these issues, and it's, well, we had a galvanized high strength steel covered with rubber going here for to allow for these members to actually wiggle here and there. And we installed also a chain block inside to be able to, to try to open the whole structure by pulling the 2 middle points together. And then we went for it. So this was basically a tryout to install this thing without a crane, and it really worked. So it was, again, there was one point between this and this where the structure was really stable, so we had to be careful. It fell a couple of times, I have to admit, and a couple of these elements actually did break. But to me, it was a really, really interesting experience. Now, I have to admit, when we installed this whole thing, it took us like 2 days to put this thing together. And in about 2 hours, when we went there, another architecture office came to site and installed a set of really boring square section, a couple of tents that you see like on, these, I don't know, when they're selling beer on the street or whatever. And so I was, scratching my head and thinking, like, we've been 2 days here, installing the rapidly, the deployable structure, and these guys just came and put this whole thing together. So I was asking myself, well, is this really just some kind of technology fetish? Are we really in love with technology so much that we don't really see the big picture? I mean, is this really a good design that is really, let's say, usable and practical, or is it just for ourselves, for our own kind of intellectual amusement? Now, 15 years later or 10 years later, whatever, I like to think about, how architecture is there not necessarily to just solve problems, but architecture is there to also somehow captivate our imagination. So I tend to not to think too much about it. I mean, how does an architecture look when all it does is to solve problems? So that's what I tell my students. If they want to do something like this, that's perfectly fine. So after completing my master's in architecture at the University of Michigan, I was still very interested in all this issue of tensile membrane structures and lightweight structures in general, and I took a job in the southwest of England in a company called Architect Landrell. Now, Architect Landrell is a company that specializes, like I said, in the design, manufacture, and installation of tensile membrane structures. And the nice thing that they have is that it's a small architecture office on top of a really large kind of manufacturing plant. So they had a steel manufacturing plant and a wood manufacturing plant, and they also confection membrane and everything. So for me as a young architect, it was a really valuable experience to actually get to design something and go down to the floor and see how heavy it was and whether it was able to, whether it worked or not, go back upstairs and keep designing. And one of the projects that I got involved with was the spiky pod. Now, the spiky pod is actually a room that holds a meeting room, for people to have meetings inside the Royal London Hospital in the Whitechapel, in Whitechapel in London, and it was designed by Alsop and Partner. So basically, they contacted us to help them design this thing So the pictures on top are basically the physical models that they gave us. And down, the pictures at the bottom are the digital form finding that we did in collaboration with a company in Bath, in England, called Tensis. So we did basically try to follow the same, their kind of main idea. And of course, with a series of push-up masts and cables and a series of pulleys, we were able to install this thing. So this is how the project looks. As you can imagine, we have, over here we have 4 legs, 1, 2, 3, and 4, and they hold inside a platform for meetings to take place. So the installation was extremely important to consider what we call, the installation method statement. Early on in the design process proved to be absolutely critical because, as you can imagine, the steel was already there, and all of a sudden we had to come with a membrane to wrap this thing around this room. So we had to kind of design this thing in 2 pieces and be able to put the legs inside, and we actually had we had an actual zipper to close the whole pod and pre-stress it. So it was really, really interesting. So like I said, in some cases we have a series of cables pulling the membrane out, and in some cases we have some push-up masts that also do that. Now, this looks like a really sophisticated, kind of high-tech project, but I find it really interesting that the design was actually done in a very conventional manner. So these slides are basically just scans from my own sketchbook in which we had to actually come up with all the construction details. And so, for example, in this case, we have a push-up mast, with some not welded here, and a head ring and so on. And this is, for example, on the other side, we see one of the steel clamps that grabs one of those huge steel legs, and the membrane is basically clamped here and pre-stressed by one in these threaded bars. So the drawings were actually, the design was done in a very kind of low-tech fashion. This is the inside view after the whole project was ready. So the Aslop and partner, they also wanted to have these blue LEDs going here, which I personally totally hated. So they wanted to have, which meant that we actually had to take electric cables going all the way up, and they also want to have these kind of submarine windows, so we had to clamp the membrane after it was pre-stressed and cut the holes and put a. So it was from the, let's say, the technical point of view, it was a really challenging project, but it was also really, really interesting for me as a young architect to be involved with. So the membrane, as you can see, is silver from the inside, and then it was black on the outside. Next to the spiky pod, we built what we called it the cloud pod. So formally, at least on the outside, it wasn't as challenging or interesting as the spiky pod. It was basically a series of steel rings with membrane, being spanned between them. The inside, however, was a different story. So at that time, this was, I'm trying to remember, this was, I think, I want to say 2004. We tried to basically come up with a strategy to install all those cladding panels inside the geometry. But then, of course, because of tolerances in the steel manufacturing and installation, because of our inability to be precise enough, we tried 3 times and we failed to install these things. So at the end, we actually had to take the table saw inside the space and just individually cut and install every single panel. So it's to find a way to meet the deadlines within a specific project. I'm talking about, I don't know, the limitations of a specific construction system. Okay, so in 2005, just moving forward, I ended up moving to Germany, to Stuttgart, and I took a job in a company called SL Rasch, which means Special and Lightweight Structures, Rasch. So Bodo Rasch is a student of Freie Otto, And he founded this company, I don't know, 30 years ago. And his office became relatively famous, at least in Germany, for the design of umbrellas, deployable umbrellas. So these umbrellas range in size from 10 feet to 100 feet. These are, all of them are square sections, so every side is 10 to 100 feet. And especially in the Middle East. So kind of like the breakthrough project in this company was made with the design and installation of the courtyard umbrellas in Medina 20 years ago. So these are basically a series of umbrellas, 2 sets of 9 umbrellas that are designed to protect the pilgrims in Medina during the day, of course, against the sun. And at night, it also somehow encloses the space and keeps the temperature from dropping. What I find really special about this project is that, in the West, we tend to disregard ornament. So ornament is something that we as a culture, we don't want to deal with. And in this office, what we found is that, of course, in the Middle East, this is completely different. They didn't go really through the modern movement. So for them, ornament is still perfectly valid. But in our case, what we did is we actually used the patches, the reinforcing patches where the membrane stresses go high, is basically where, and the seams of the membrane and the belts that take the forces on the sides and so on, those are absolutely necessary. You couldn't build this thing without them, but they become the ornament layout of the whole design. So they're both somehow ornament, but also completely necessary. So the project that I wanted to talk to you about today is actually are the umbrellas not for the mosque, not for the courtyards inside the mosque, but a series of umbrellas that we built outside the courtyard, outside the mosque. This is a really big courtyard. It's about 1.5 million square feet. And what we did is that we designed 260 umbrellas. Every side of the umbrella is about 26 meters in diameter. Every side is 26 meters, so I don't know how much that is in feet. Right, so there are basically 2 heights. So when the umbrella is closed, they all have the same height, but when they open, they have different heights so that they overlap, which was an improvement from the previous project. And when they close, they actually match the height of the facade of the mosque. So the membrane itself had to be produced by the Swiss company CCA, and is pure PTFE. And the reason of that is because PTFE allows for the whole membrane to be opened and closed 1 million times without losing any tensile strength. So it's uncoated, so meaning that we had to actually sew all the pieces together, all the patterns. The membrane is, of course, curved in 2 directions, so to achieve that shape, we need to have patterns, and because the membrane wasn't coated, we had to actually sew the things together. So it was a really interesting kind of like design development process. But anyway, so the whole idea of the project is to basically protect the pilgrims from the sun around the mosque. So this is a plan of the whole mosque. Here you can see the old umbrellas here and here. Now the new project was actually that. So 260 umbrellas that could be actually deployed individually. So every umbrella could open and close, or every sector could be closed and opened and closed independently. And so you can see what it's all about. I mean, we're talking about 120 degrees in the summer, and the second we install the first umbrella, that's where people actually go and sit, obviously, in the shadow. In fact, it was interesting because these lights were also designed by the same company, and apparently what they told me is that when they installed the original light, the people were actually sitting along the shadow of that post, of that individual mast. So of course, this, the umbrella was a huge improvement. So this is the size, the facade, let's say, of the umbrella. It was built in collaboration with a crane company, a German crane company called Liebherr, which I've seen many cranes in the US as well. So again, when the umbrella was closed, they all had the same height, but when they opened, they were actually overlapping. So this is a series of pictures that that show how this thing opens and closes. You can see the umbrella being held by cables here, so that it doesn't hang like that and get trapped by the cladding of the arms. Right, so it continues to open, puts more, and then it's pre-stressed. So it was a beautiful design, I will argue, and you can see this is the only kind of corner open to the space. We see the entire umbrella. Every umbrella costed about 2 million euros. So it's like 3 million per umbrella. And now what's interesting is this is like the gossip, the inside knowledge, is that this was built, I'm trying to remember, it was a really long design process, so the whole project took like 6 years. But at the time, this was the same time where the bird nest was being built in China and the Olympics and everything. So there was basically there was no steel in the world. So we put an order to build these things, and it's like, well, the waiting time is like 2 years. So my boss he actually traveled to India and secured a series of pipes, then changed the design and sold the pipes to his client. And just in that transaction, I can only imagine how many millions he made, just kind of reselling steel. Yeah, but that's business. That's how it works. Of course, it doesn't really rain that much in Saudi Arabia, but when it rains unbelievably hard. So it rains for like 3 days a year, but it really kind of rains a lot. So the umbrellas are also there to collect water. So rainwater gets basically collected here and dropped here, and then there is an inside kind of gutter that and the water is actually saved underneath. Yeah. So yeah, we have basically what we call the diagonal arms. We have the central arms, and these are what we call passive arms. So the main arms are mechanized, right? They fold twice. So this is not just like a simple umbrella that is folded that way, but it actually folds in that way. So, and the whole idea was that you can then cover a lot of area without having an umbrella that is really tall. And also, you can imagine with a continuous speed, the arms, as they move down, they actually increase speed, even if your engine is moving at the same, So when you want the umbrella to go like at the beginning or at the end, when you actually want the umbrella to move slower, that's when it moves faster. So the main arms are folded twice, and they go in that way. And then these are basically called passive arms, and they're just a pin connection, and the membrane itself just opens them up. Okay, so as David mentioned, in 2005, I opened my own small architecture office called the Studio for Lightweight Design, or Studio LD, and we had the chance to do a couple of projects just before I came here. The first project was the Puruklu floating marinas in Turkey, and we did this in collaboration with a Canadian company actually called Structures Marine. So Structures Marine is a company that specializes in the design and fabrication of floating marinas. That's it. That's all they do. But they had this kind of high-profile project, actually 2 projects, in Turkey, and they contacted us to kind of design a system that allows them to cover these marinas, these floating marinas. So the challenge was to basically design a structure that could take about a deflection of plus minus 3 feet. So plus, you can imagine waves up to 3 feet kind of deflecting all of these. So we had to design a geometry that allowed for these arches not to collide with each other, and to the whole roof to be as flexible as the floating marinas. So we came up with a design of something that we call the flexi block, which was basically a brick made out of rubber with a steel plate inside that allowed for all of these kind of elements to move and still be firmly secure, but to be able to move up and down. So the flexi block is basically always connected at the bottom of these extrusions. What we did is we designed the entire thing by using the construction materials that this company produced. So the entire floating marina was aluminum extrusions, basically, the whole thing. So we used the same profiles that they had to create these arches, and then spanned a polyester PVC membrane between the arches, right? There are actually a couple of details, and when I see this picture, I cannot avoid looking at them, but I'm not going to tell you what they are. Yeah. So another project that was really interesting was 4 years ago already. The architecture office called Helen and Hart, they won a competition to design the Norway Pavilion in the Expo 2010 in Shanghai. So their design, these are basically renderings, these are the pictures from the architecture office, from Helen and Hart. And their idea was to kind of represent the forest that they have in Norway, and to create these kind of pavilion that was really luminous and whatnot. And so they had the idea of a series of translucent roofs that collected water, and they had like solar panels on top and so on. So, and they also had this fantastic idea, and I think some people argued that's the reason why they won the competition. That it was basically thinking about what to do with the pavilion after the expo was over. So typically, in a typical art exposition, a universal exposition, all buildings either stay there and get reused. So what it was before, let's say, the expo pavilion of a particular country becomes an embassy or an office building or something like that. But as it happens, there's a lot of kind of more lightweight structures that get basically destroyed. So what they proposed was to have all of these trees together, and then a year later, in 2011, to basically disassemble all the trees and send them around the world as gifts. So the idea will be that we in San Francisco here had a tree from the Expo 2010, the Norway Pavilion. And as you can imagine, in Norway they have a lot of high-tech technology in terms of wood. So all those trees were glulam structures. And again, they could have like solar trees, and they had an air tree, and they had water trees, and they had a whole series of very kind of sophisticated abstractions of and ideas about what they wanted to build. And so this is basically just a rendering of the roof. So we told them, well, why don't you use a membrane structure for the roof? We actually talked to Jan Knippers, who's a professor at the University of Stuttgart, and who had a larger office and was able to, we were under their insurance umbrella. So we worked directly with Held and Hart through Knippers Helbig is called the company. In any case, so we did a form finding in Rhino membrane, which my students from my tensile membrane structure seminar know really well by now. So we did a digital form finding of the membrane, and basically gave it to the architects, and they loved it. So basically they said, well, now we can still follow the same idea, and this will be, let's say, in New York or Chicago or, I don't know, Helsinki, and this will be a tree. So these are basically all the different revisions that the 3D model went through when we joined the team. So these basically show you all the different variations. So every time a tree changed, we had to do another form finding technique, and then the membrane had to change, and they had to do so we did a couple of hundred, revisions until we all agreed that it was fine. So the glue lamp trees were prefabricated in Norway and sent to China. And we also did the installation, so we basically moved over there and supervised the installation. You can see the trees are actually white because they're protected in plastic, against scratching. And for us, it was actually a really interesting design because we had to come up with a series of individual members. This is basically what we call an erection joint. So it's there because the pieces of membrane are too big to be able to be installed in one single go. But the idea was that this, what we call the 4-point cell, was able to remain intact after the exposition was over. So the idea was to basically cut all of these extra membrane right after, and basically send again every individual tree someplace else. So this is how the pavilion looked one day before the expo opened. And if you actually Googled pictures of this pavilion, you will only see these pictures. Now, there's something interesting. There's no people here. There's not a single person. This was the day before the expo opened. The pavilion was ready. Everybody was really happy. Yeah, and this is when how important it becomes to really get yourself as a designer, as an architect, familiar, let's say, with the behavioral properties of construction materials. So after this was over, the people who were installing the flat screens inside the pavilion, they realized that there was actually too much light into this material. This is a material that is 10 times more expensive than the standard kind of polyester PVC. This is pure, it's a coated Teflon. Again, it's the same company who did the umbrella membrane. So that night, they actually decided to send somebody on the roof with a bucket of paint, and they painted the entire pavilion from the top, trying to get the membrane to be slightly more translucent, to get a lower degree of light translucency. And this is how the pavilion looked next day. So basically, the entire idea of sending trees around the world and all of that is like, okay, just you can trash this whole thing. So yeah. So of course you don't find this picture online. I guarantee that you always find this without people. Well, I don't know. I mean, it might be out, but this is the story. So, right. So in 2005, I also got the opportunity to actually teach architecture at the University of Stuttgart. So obviously since the 60s, the University of Stuttgart has been a hot spot for the design of lightweight and sensor membrane structures. This is a field, like I said, in which the behavioral properties of building materials often somehow reinforces the conceptual basis of a proposal, of a project. So in a sense, form and materiality and, let's say, structural performance are linked together. So these pictures you might have seen before show a series of form-finding techniques developed by the Institute of Lightweight Structures in the 60s by Fray Otto. Now that institute is called the ILEC. So before it was the IL, and now it's the ILEK. And the new professor is Werner Sovek, who's also famous. And so the idea behind these models was basically to learn from nature and try to comprehend a little bit the performance of a structural system. And in order to develop a construction logic that somehow links, again, like I said, material, form, and structural performance. And it's also with the idea of saving material, of designing something that is light and beautiful at the same time. So a project that I wanted to show that really was, from my point of view, was absolutely one of the most successful projects that I've seen, was actually designed and built at the university campus by Jan Knippers from the Institute of Structures, the ITKA, and Aji Menges from the Institute of Computational Design, and a big team of people who included, Moritz Fleischmann and Julian Linhardt, who I believe is going to come next summer to teach in the 333 studio, and Simon Schleicher, who was the project manager, and a series of other people. And this was a project, it was a research pavilion that was basically developed in 2 phases. So the first phase, we asked our students to basically, we gave them plywood, and we said, well, what can you do with it? So the concept is just to try to explore the potential and discover the limitations of a building material, and use that as the conceptual basis of your design. So students spend the whole semester in a studio just playing with plywood and seeing what they can actually build, and really thin wood and bending and cutting and so on. And we actually chose the proposal from one of the students to build next semester. So next semester what we did is at the university, it was a 6 millimeter thick plywood, so it was bent, and these elements do not only measure let's say how much pre-stress is here, but also the moment on the basis, the reaction forces. And with that, a computer model was created in Sophistic to look into the structural performance of the pavilion. The whole thing was also done parametrically. So the team of the Institute for Computational Design had somehow varied the number of stripes inside the model, how many plywood stripes, also the geometry of the base, whether it was circular or whether it was a more kind of flower arrangement. And of course, all the individual pieces were also not only fully detailed, but also analyzed structurally. What's interesting is, the team actually used the robotic arm at the University of Stuttgart to cut all the pieces, and which facilitated the erection of this pavilion, because of course, if we had to actually cut all of these pieces by hand, it would have taken a long time. And now from my point of view, that's actually not that interesting. What is interesting, however, is the fact that we as architects, with the development of new, let's say, digital fabrication techniques, we are now reclaiming the manufacturing process. We're taking control of a project beyond let's say, the completion of construction documents. So all of a sudden, an architect potentially doesn't need a contractor anymore. He can actually take control over the entire design and manufacturing and installation process, which I think is truly fascinating, because it's somehow bringing back materiality, into the realm of architecture. A series of projects of pictures of the construction details. This project won the I think it was called the Mies van der Rohe Design Prize in Stuttgart, which is a big deal, and also the Detail Magazine Prize. So it was published everywhere. I'm sure you've seen it. And again, it was designed by a collaboration between Aji Menges and Jan Knippers from the Institute of Computational Design and the Institute of Structures. So these are our students putting this thing together. And this is not a model. This is a real picture of the whole thing. So the design, the pavilion was actually intended to be there for a whole year. But then winter came, and this is open space, so people were really afraid about nobody had actually tested let's say, how much structural integrity was left after plywood was exposed to the weather for so long and a lot of snow on it. So people at the university were a little bit nervous, so they actually decided to dismantle it before the winter came. So, but it was I think from my point of view, it was a super successful project because again, it really took into account the behavioral properties of a construction material as a starting point, as something that is really reinforcing the concept of a proposal. So I've been trying to basically to talk to my students about my teaching philosophy. So I just wanted to show you really quickly a couple of design studios that I ran at the University of Stuttgart. These shouldn't take too long. So the first one is the Paris-Dakar camp. So the Paris-Dakar race was actually moved from, you might actually know about this, was moved from Europe and Africa, Northern Africa, to South America. So it's basically a team of racers get into one of these little trucks and with a racing car, and they have to kind of navigate through all this amazing landscape, and they also have to spend the night there. So the design challenge was, well, I asked my students, how can you propose a camp to for a series of people, 12 people, to spend the night in the middle of nowhere? And this is a camp that needs to be reinstalled every so often. So these are basically a couple of my students designed, talking about lightweight structures and using the cars as means of installing the whole thing. This was basically another proposal. So the installation process becomes also super important. Yeah, this is the physical model. And of course, all the detail. So this is also something that we do here also at the California College of the Arts in our comprehensive building design studios. That is to try to prove to our students that you can be responsible in a way of looking into, let's say, all the construction systems and all the materials and all the details of a proposal, and at the same time be creative, think outside the box. So a mobile health clinic. In Africa, there are some villages that they're about 2 days away from medical facilities. So the idea, and nowadays you have a series of ambulances who drive between these villages. But these ambulances, they don't have any resources, any infrastructure attached to them. So we say, well, what if we had to design a camp? A mobile health clinic that had to be moved every so often from village to village. And so these are basically proposals from our students, right? So this one, for example, was a deployable, inflatable structure that was somehow packed inside the ambulance, and it was surrounding it and so on. A couple of other projects. This worked like as an accordion and had a tensile membrane structure on top. So talking about the stability of the construction and being somehow going a little bit more in detail about what exactly means to propose a project like this. Another one was called the Arctic Lab, as you probably know. A couple of years ago in Svalbard, I don't know how to pronounce that, I'm sorry, in Norway, there's an island, and they actually built a seed bank buried inside a mountain. So inside the mountain, they have a series of chambers in which they now collect and store all the seeds used in agriculture around the world. And the idea behind it is to basically guarantee genetic diversity. So, climate change, droughts, floodings, diseases, whatever, we tend to always cultivate the same kind of crops. So in this case, we still have at our disposal a higher, let's say, diversity in terms of genetics if we need it. So I asked my students, well, what if we have to have a lab that can test these things? And the whole idea was to try to get them to think about prefabricated system, how you assemble something together, how you bring it to a remote location, and also to somehow responsibly design a building that takes care of a really cold environment. So this guy, a student of mine, designed a floating kind of buoy. You know, there was an entire building, and these are the plan drawings. And the whole idea was that in the winter, frozen water was actually warmer than the air temperature. So he was actually, sinking the whole building in the sea, to insulate against cold. So I thought it was really creative. Another student, let's say more conventionally, was thinking about the maximum size of a prefabricated element to be shipped inside a shipping container and installed there. So she designed this little building and developed all the construction details and so on. Then the last project I wanted to show is again in a very kind of remote location in the desert in Saudi Arabia. So it was a station that explored the potential of a building to produce actually food in the middle of the desert. So it's something similar to what my students are doing right now in my comprehensive building design studio. So a series of buildings. This one was for living. No, this one was for production of wheat, and this one was for living, right? Renderings and a couple of views. So I'm also teaching right now a materials logic, material systems seminar. I wanted to show you one picture of our review today. This was taken right outside just a couple of hours ago. The idea of the seminar is asking students to develop a construction logic that basically I gave them typical construction materials, plywood, 2x4s, drywall, and so on, and ask them to develop a construction logic that takes into account the potential and limitation of those specific construction materials to build somehow a cube that is 16 inches by 16 inches by 16 inches. This is actually a design studio that I once saw at Rice University, and I think it's a really fascinating design exercise, because first of all, it asks students to work in scale 1-to-1. So these are not abstractions, these are not models, they are autonomous pieces all by themselves. Students have to basically control the project all the way from an initial sketch to a final erection. They work in scale 1-to-1, and they work in direct contact with real building materials, right? So this is also something that I've been running in my membrane structure seminar. So just really quickly, a couple of examples of proposals that my students have done through the years. Membrane structures are, as I mentioned before, projects in which the behavioral properties of the materials become really, really important and often support the concept of a design. So just a series of projects. All these pictures were exposed at the last year's exhibition faculty show and the Oakland campus, the CCA. And I wanted to show you a couple of pictures of our charrette, thank you. The design charrette. So again, in this case, we can see how architecture students really typically, they really respond when you ask them to work directly with construction materials, no matter what they are. And you give them even a very short period of time to design, build, and erect something. So this was a design charrette that lasted 3 days last fall. We gave students a couple of translucent plastic and tape, and they were able to come up with really fascinating designs. And in my tensile membrane structure seminar, we're currently working, this is basically the final project. This is a proposal to cover the entrance courtyard of our building. So we've been working together with management, the CCA, to actually build this tensile membrane structure. It's a cable structure with a tensile membrane structure on top. Okay, so just to finalize, my teaching philosophy, my professional philosophy, the way I see architecture is not really trying to transform architecture or the education of an architect into some kind of a trade school by overemphasizing construction principles and ignoring other very, very important concepts and ideas, but it's really about recognizing the importance of recognizing that architecture is still firmly anchored in material reality, and that the more we know about the more we consider technical issues as part of a creative landscape, the more successful we could be. Thank you.